Bismillahirrahmanirrahim. Welcome students. In the today's lecture, we will be discussing the combinational logic. In the previous lecture, we discussed the exclusive OR and the exclusive NOR function along with some of their properties. In the current lecture, we will be starting a new topic which is known as the combinational logic. Generally, any given digital circuits are categorized in two types of circuits. First one is the combinational circuits, while the second one is the sequential circuits. First, we will be discussing the combinational circuits because till now the most of the circuits that we have studied so far lie in this combinational circuits category. We define a combinational circuit in a way that the all the outputs are the functions or of the inputs, or you can say that they are dependent only on the current input of the system only. Say if you change the input, then the output will also change. The combinational circuits don't have any memory or storage element, and so they also don't have any feedback mechanism involved in it. How do we define a feedback? We will discuss that in more detail when we will be discussing the sequential circuits. In sequential circuits, we have memory elements. In these memory elements, there is a feedback involved. Feedback actually means that the output of a system does not only depends upon its current value but also on its past values. So we have to maintain the past values of the previous circuit too. So that's why sequential circuits involve a memory element or a storage element in it. We will be discussing the combinational part now, and from the next chapter we will be discussing the sequential circuits. Say we have a for a sequential for a combinational circuits, we have a n input variables and m output variables. Generally, first what we do is we define a 2 power n input combination for all the inputs. All the combination will be defined as 2 to the power n, and for each of these 2 to the power n we will have a one or more than one output variable. The each output variable will be actually be representing a certain specified function. Say we can say is f1, f2 or f3, and in reality the f1, f2 and f3 actually represent some proper function or meaning. They have a certain meaning, like they could be an output of an adder, they could be out of a multiplier or subtractor. When we design a combinational logic system, we will have a set of inputs. Say we have a n inputs, and we would have a m outputs. Each of the m output would have only value of a unique value at each combination, just like we studied in the last chapter, that if we develop a truth table for this combinational logic circuit or any given Boolean function, then that for that Boolean function for a given combination, say if we have a 3 input system, then we would have 8 combinations in the input. For each combination or for each minterm, we would have a value of either 1 or 0 on the output of the function. Similarly, this happens for the next function and for the next one. Combinational logic is a circuit in which we have a combination of outputs which are dependent on the current values of the input. We will be discussing a lot of these systems in our this part of the course. We will be discussing the adders, subtractors, comparators, decoders, encoders, and the multiplexer. We will also be discussing a few more details regarding these things. Most of these combinational logic circuits are also available in the IC packaging form too. Means you have a separate adder or subtractor in a form of separate ICs, just like you have specific ICs for exclusive OR gate or for the AND gate or for the OR gate. We will be discussing two type of approaches for the combinational circuits. First is the analysis thing. In the analysis part, what we do is we try to figure out what the function of this circuit is from a given circuit diagram. We try to understand that what kind of the circuit we are dealing with. So, in this analysis part, we will be given a circuit diagram, and then from that circuit diagram, we will follow certain steps, and then from certain step, we will identify what the functionality of this circuit is. There are certain steps to determine these things. The first step is that we should make sure that it is a combinational circuit and not a sequential circuit. And how we can identify it from a circuit diagram? We can identify it from a circuit diagram in a way that it should not involve any feedback path. Means that output of any given gate should only be dependent on its current input, not on some previous inputs or the value of some other output gate which is yet to be calculated. The second thing is then we derive the Boolean functions for this path, and from that Boolean function we can then derive the truth table, and from the truth table we can then identify that what was the main function for this process. Why was this circuit designed? So this thing is known as the analysis procedure. We will try to understand this process with the help of an example. Suppose we are given a circuit diagram like this one here, and using the analysis procedure, we have to understand what this circuit is for. So what first thing we do is that we mark the important points on this circuit and name them using certain naming conventions. Say what we do, first thing is we name this output as say T2, this output gate as T1, this output as F1, and this output as F2. We can clearly see that what are the inputs and outputs of the system, because it is clear from the figure that F1 and F2 are the outputs while A, B, C are the inputs to the system. So first we have identified the inputs and the outputs of the system, and then we have marked the important points of the system using any values. Say we have represented it as T1, we have represented it as T2. Similarly, we have represented this as the T3. For the first one, say if we want to determine the values which we can directly determine or easily determine, which are not dependent on the other parts, like this gate is very easily calculated. It's just the AND operation between A and B. Similarly, this is the AND operation between A and C. This is the AND operation between B and C. So we can easily write the output of this equation, and this the output at this point is equal to F2. So we can easily write the equation of F2 as this one. Similarly, we can easily write the value of T1 and T2s. T1 is just the OR operation between the three input variables A, B and C, while T2 is the AND operation between the three input variables A, B, C. Now if we want to determine the other values that are available in the system, actually the value of F2, T2 and T1, these are very easily calculated. So first we have calculated them, but we can also calculate the other points too. Like we can also calculate the value at the output value at T3. For the T3, if you write that here as, it's basically the complement of this F2 function here. This is the F2 function, and it is AND with the output of this gate, which is represented by T1. So this will be represented as this one. And the final output of F1, the function 1, is the OR operation between T3 and T2. So first what we do is we just try to write or figure out what are the Boolean functions for the Boolean equations for the given outputs. So we have expressed both the outputs here. But for the first step, what we have done here is that we have expressed the f1 and the f2 in terms of some intermediate variable. The f2 output is very clear, it's just only dependent upon the input, so we have written the inputs here. But f1 is not that straightforward, because if you look at that, f1 is dependent on two intermediate variables which we have just introduced. One is the t3 and the next one is the T2. And then you can also see that T3 is also dependent upon another intermediate variable T1. So F1 is not just writing T3 plus T2, but it will involve many other terms inside it. Now, if we want to express this F1 fully, that what expressions are involved in it, we need to represent the terms that are representing the T3 and the T2 terms here. We know that T3 was the AND operation between the complement of the F2 function and the T1 term. So we can write it as like this one. And we then the T2 was clear that it was AND operation between the three input variables A, B, and C. Now, if we express the value of F2 complement here, because we have to represent the F2 here. So this is the value of F2 here. This is then the value of the T1 here. And now what we need to do is we need to solve this expression. This is actually the complement, so we can solve it through the De Morgan's law. By solving it through the De Morgan's law, this would be represented as A complement or B complement, and this term will be represented as A complement or C complement. Similarly, all the other terms. And then we just need to simplify all these terms. We can open up these brackets to solve these terms, and the final result of this is equal to f1 is equal to this thing. So this expression represents the final value of the f1 function. We have already calculated the value of f2 function. In the future lectures, we will be discussing the full adders and the half adder things. And when we will reach there, then you could see that basically these F1 and F2 are representing the outputs of a full adder. There are two outputs for an adder. One is the sum and the carry. The F1 actually is representing the sum, while F2 is representing the carry. You can see that it is not clear or visible from the circuits that what the circuit was doing. But if you calculate all the expression, and then you could say come up with the result that this expression is actually equivalent to the sum expression or the carry expression. Even when we will study that topic in the later lectures, you will see that the result isn't quite the same as of this expression. We need to do some modifications in it to represent it. Actually, it's the equivalent form of the sum and the carry term, the F1 and the F2 terms. The more better way to understand this thing is to draw a truth table. Because from the truth table we can judge quite appropriately that what was the main functionality of any given function. So because there are three inputs involved, A, B, C, so first what we need to do is we need to write all the combinations of the three input system. So we have written the 8 combinations here. And then what we do is we try to mark all or calculate all the intermediate variables and the output variables that are involved in the system. Basically, there are two outputs, F1 and F2, while rest are the intermediate variables that we have defined for our own easiness. So we keep on calculating each term. We know what's the value of F2 from the circuit. We can easily identify that. And even from the expression that we have calculated in the last slide, we can calculate the value of F2 from there. And then similarly, because in the calculation of F1, you know that F2 complement was involved. So we need to also calculate the F2 complement here. So that's why we have calculated here. And then we will calculate the T1, T2 and T3 intermediate variable here. We have already written their equations, the T1, T2's and the T3's equation. We need to just express them in the form of the output. So we have expressed in the form of the truth table like this. And now if you compare this table, specifically the F1 and the F2 term with the four ladder equation, then you will know that this is representing the F1 is representing the sum, while F2 is representing the carry. Then there is an other way to look at any given circuit. That is mainly, you can say, we call it a synthesis procedure. In synthesis procedure, we do the opposite of basically the analysis thing, because in the analysis part, what we do is we start from a circuit diagram, and then we end up with an Boolean functions that represents a certain functionality. In the design approach or the synthesis approach, it is the more straightforward or the of the approaches which we are used to. In this approach, we would be given a certain problem, and from that certain problem, we first identify or specify what will be the inputs and the outputs of the system will be. And then we assign certain variables to the input and the output, and then we draw the truth table between these set of the inputs and outputs. And from the truth table, we can represent them in form of say min terms or the max term, and then we can apply the Boolean functions or the simplification procedures we have developed using the Boolean algebra or with the K maps. And then we, from that expressions, we represent them in a minimized form, and from that minimized form, we represents the circuit in a form of a logic diagram. Actually, these are the steps we were generally following in the last few lectures to derive a certain Boolean functions. Now we will be studying them in a form of a say more systematic way, using step 1, step 2, step 3 up to step 6. We will try to understand the synthesis part of the design part through an example. This is an example of a code converter. We have discussed many different kind of binary codes because we have studied that different hardware uses different kind of architectures, and each architecture could be using a separate binary code. So if we want to interface say two different hardwares, one hardware is say dealing with the BCD code and the other hardware is dealing with the XS3 code. We need to have a converter so that we could appropriately communicate between them. A converter's job would be to convert a simple BCD code to say an XS3 code. So in this example, what we are trying to do is we are trying to develop a code converter whose purpose is to convert a simple BCD code into an XS3 code. We know that we have studied both of them in the chapter 1. So from the table of the chapter 1, you can just recall them and have a look at it, what was the BCD and the XS3. Now we have the first step. We defined what was the basic functionality of our code would be, and now we need to define what will be our inputs and the outputs of the given system. So first we have to define the inputs. We know that BCD is represented in a form of 4 input system or 4 variable system. We are defining each bit as a separate digit in a form of an ABCD network. So we have 4 variables ABCD. Each combination is representing an equivalent decimal number. We know that the BCD number starts from a 0 and the last digit that is represented is equal to the 9. So these are the BCD codes, set of BCD codes. Similarly, we can also define the XS3 code. We know that for the XS3 code, it is equivalent to adding +3 to the decimal or the binary equivalent of the number. So from these are the equivalent XS3 code. What we have done is for the BCD code, we have represented each input variable as A, B, C, D, while for the XS3 we have represented it as W, X, Y, Z. So basically this is the set of BCD is the set of input. We have 4 input system, and XS3 is representing a 4 output system. So we have a system in which we are having 4 inputs A, B, C, D, and we will be getting the 4 different outputs W, X, Y, Z. Input is representing the BCD, a sequence code, while the access3 will be representing the output code. And if you remember that when we studied the BCD code, we studied that BCD code are only present for the combination till 9. After the 9, all the combinations are not used in the system. They are the unused bits. We will be also be utilizing these unused bits in our system design too. Now we will need to represent the simplified Boolean functions. So how we can represent them? We can have seen the truth table, because from the truth table you have seen that we have the 4 input system and we are have achieving 4 outputs. So what we do is that we first consider only the one output, and for that one output we draw an expression, and then we minimize that expression. And similarly we then move on to the next output, and for that next output, depending upon the inputs, which are the 4 inputs ABCD, we represent it is in a form of a Boolean function, and then we minimize that Boolean function, and similarly for the third and the fourth time. So we'll be moving on with the each output separately. So for the simplification, what we do is first we consider that we are having a 4 input system ABCD, and we are getting only the say Z as the output. So in the first case, we are getting only considering the Z as the output. From the truth table, we can see that when it is happening and how we can actually draw or simplify or express it in the form of a simplified expression. This can be expressed in a way that if you consider all the min terms and just check that on which value we have Z equal to 1, and then that would be representing the min terms that are for this function Z only. So if we express this Z as, we can write it as here, because if you see the truth table which we discussed in the 2 slides below, we have 1 here at M0, M1, M4, M6, M8. We have 1 here. And you can see that because for the BCD combinations, the number of combinations after the 9, say 10, 11, 12 up to 15, they are unused in the BCD format. So we have option to use them as to our own convenience. So what we do is we mark them as the don't care condition. If you look at this, from M10 to M15, we have marked all these minterms as X. It means that if they are helping us in minimizing the function, then we will be utilizing them. If they are not, then we will just ignore them. It is just like using the don't care approach, which we studied for a 4 variable K map. So we have taken the ABCD as the inputs of the system, which are representing the BCD code, and we have just taken the first output, which is was represented as Z, and we marked all the spaces and ones as ones in which in the truth table was value Z was equal to 1. And then we have also written the don't care conditions, because these are the bits which are not used. And then we will move on to the simplification procedure. So if you want to simplify this K map, it is very easy. You know that we have to first solve the bigger ones. We have a combination of 8 adjacent ones here. So we can, if we use this and this don't care condition, then we can easily form a combination of 8 adjacent ones, and then these adjacent ones are represented by the term D complement. So for the first one, what we do is, for the first output, we can simply represent it as in the simplified form as Z is equal to D complement. Then we will move on to the next output, which is represented here as Y. For the Y, what we do is that for this output, we again mark all the values which were having 1 at the truth table. So at Y, so we marked all the values which was M0, M3, M4, M7 and M8, and the don't care conditions remains the same here. So now we will again try to minimize this 4 variable K map system, and we can utilize all these X as up to our convenience. And if you see that there are no 8 adjacent square possible, So we will move to the, if we have a combination of four adjacent square, which you can see that there are two kind of four blocks here. One is this one, and the next one is the this one. So we will be representing them as the minimized expression form. So this will be representing as C complement D complement, and this adjacent set of adjacent squares will be represented as CD. So this is the second expression. For the third expression, if we have to calculate the value of output value of x, the x output is calculated as by first placing all the ones there. So we have placed all the ones, and then by utilizing all the don't care conditions that we have in it to minimize this whole four variable k-map system. And if you can see that we can easily minimize it, we can have adjacent squares like this one. This is forming an adjacent square with the bottom terms here, and similarly we can also form adjacent squares of four ones like this one, and then we will have adjacent squares of two ones here. So all these expressions are represented here as like this. And for the last one, for the W, again we will follow the similar strategy. First we will place one on all the places in which the truth table which have value of 1, and then we will try to utilize the values of don't care conditions that we have here to minimize the expression. And again from here we can see that we have a adjacent 8 adjacent 1 here. So first we will try to minimize this expression. This will be represented as A here. Then we need to represent the other two terms. Then we have one combination here of 4 adjacent 1, and then one combination here. So W is represented as this one. These were the expressions that we calculated from the K-map. If you just look at this expression, we can further solve these expressions a little bit, or we can express in a way that our circuit could be a more simplified form, you can say. Look, because this is the C complement D complement, from the De Morgan's law we can express it as C plus D complement. So we can express it as this one. Similarly, for the X term, we can take this C plus D common from the first inputs and the last one. So we can express it as this one, C plus D here and C plus D complement here. And similarly from the last expression, then again what we can do is we can write we can take the B common here as this. So these two terms could be expressed as C plus D. So if you just look at this, these expressions are actually representing the same things and above. Just we have find out that there's a term which is known as C or D, which is almost using in all the terms, the Y, X, and the W terms, which are we are utilizing in all the terms. So we could make it as a more convenient circuit from this term too. So if we express this in a form of a circuit diagram, then we can easily express it. We know that what is the value of W from the last expression. We can just derive all the values W, X, Y, and Z. Z was very easy. It was just the D complement. So it's here. And from the next three expression, we have seen that there was term common for all the term, which was C plus D and C plus D complement. So we have taken the output here. And this output, because is utilized in all the circuits, so we have represented this term separately here. Otherwise you can also avoid this thing and just draw the first part which we discussed in the last slide, which would also be the same or result in the correct circuit. This would just give us a better understanding of the circuit. Otherwise the both expression or the both set of expressions or the circuits are fine. So from here we represent all the outputs Z, Y, X, and W. So actually these now represents the code converter outputs. We have a input here as A, B, C, D, it means that we would apply a binary equivalent code here, and that code, this whole circuit will generate an equivalent access 3 code at the output. So this is a complete example of a code converter from BCD to access 3. Kindly do read these pages from the book for better understanding. Thank you.